need someone's hand to lead me through the night. I need for someone's arms to hold.
Okay, problem number 3 asks us to find the exact solution, aka particular solution, of the IVP, initial value problem, and the interval of existence. So let's look here. The first thing we have to do is we're looking at, okay, so we have an initial value problem. So this is our ODE that we're starting with, right? This is our initial condition. I like to label things just so I can kind of organize the information I'm given. And ultimately, we're going to find a particular solution. So we're going to find the general solution and then utilize our initial condition here in order to pin down that exact constant, right? So to find the particular solution, and then at the end, we're just going to analyze what is the interval of existence of our solution. Okay, so we're going to start with our ODE, like we always do. So dy over dx in this case, because we have an x here, is equal to sine x over y. Okay, so to separate these, all we have to do is multiply by y on both sides, so we get y dy, and multiply by dx on both sides, so we get sine of x times dx, and then we're just going to integrate here pretty simply. So we get 1/2 y squared is equal to a negative cosine x plus c, okay? And then at this point, before I try to even solve for y, I'm just going to utilize my initial condition, okay, to pin down this c, and then we'll go from there and try to solve for y. Okay, so if I do that, I'm going to come up here, and this initial condition means that when x is equal to pi over 2, then that means our y is equal to 1. Okay, that's what our initial condition tells us. So let's plug in those values for x and y at the same time to figure out our c. So we have 1/2, instead of y, we're going to plug in a 1 here, squared is equal to negative cosine, and x is a pi over 2, and then we have plus c. And cosine at pi over 2, our x value at pi over 2 is going to be 0. Okay, so our c is going to be equal to a 1/2. Okay? So now that we have that, we can plug it back into this in order to form a particular solution. So we have 1/2 y squared is equal to negative cosine x plus, and now we're plugging in a 1/2 for our c, right, because we just found that out. Okay, so now we're here, and we need to solve for our y explicitly, okay? So in order to do that, we're just going to multiply by 2 on both sides. Okay, so if you multiply by 2 everywhere, we get y squared is equal to a negative 2 cosine x and plus a 1. All right, and let's continue this on the next slide. So we have y squared is equal to negative 2 cosine x and then plus a 1. Okay, and then this is the same thing. I'll just rewrite it. 1 minus 2 cosine x. That looks nicer. And then we're just going to square root both sides. So we get y by itself is equal to plus or minus the square root of 1 minus 2 cosine x, okay? And then in order to determine which one we need, remember we can't have this sign ambiguity here, so we're going to use our initial condition, which was y of pi over 2 is equal to a positive 1, okay? So now if we plug in pi over 2 for x, we should get, we can determine which sign we need there. So y of pi over 2, which should be equal to a positive 1, right, is equal to plus or minus, and we'll decide on this step here, 1 minus 2 cosine pi over 2, and again, this quantity here is 0, so we have square root of 1, so we need this plus sign here in order to match the left side, okay? So we're going to take the plus sign 1, so our y of x is equal to positive square root of 1 minus 2 cosine x, all right? So this is our exact solution, or our particular solution. There are a couple different ways you can refer to it. So we have our particular solution, and now what we need to do is study the interval of existence, okay? And we'll start that on the next slide. So here's our particular solution. So we have the positive square root of 1 minus 2 cosine x, okay? And here's just a refresher. Our original ODE, our ordinary differential equation, was y prime is equal to sine x over y, okay? Alrighty, so interval of existence. So that just means the largest interval over which our solution is defined. So this is our solution, right? So first of all, it has to be defined, and then it has to remain the solution when we plug it into our ODE. Okay, so to address the first part, our solution is defined when our square root actually exists. So you can't take the square root of a negative number. That's the whole crux behind when a function involving a square root of any sort, or a square root is defined or not. Okay, so this just means that whatever's inside has to be greater than or equal to 0, right? Because I mean, you can take the square root of 0; it's just 0. But I'll just write a huge but here. If we look at our ODE, our ordinary differential equation here, our y, let's say the inside does equal 0, okay? And then we have y is equal to 0. So y would then be equal to 0. And when we look at our ODE here, then we'd have sine x of some sort over 0, which is undefined. So we cannot have that, because that would mean that our solution is not in fact a solution to the ODE here. So we cannot have y equaling 0, so that means we have to get rid of that guy here, okay? That's why I just blotted it out. So basically we're working with this. 1 minus 2 cosine x is strictly greater than 0, okay? That's important to note, all right, for our interval of existence here. Okay, so now all we have to do is just find the intervals on which this is true. So then we would just solve for x. So let's add this 2 cosine x to the right side. So we're going to add it. Okay, that goes away, and then we get 1 is greater than 2 cosine x. And if we divide by 2, we get cosine x is less than 1 over 2 is less than a half. So let's look at our unit circle. Handy dandy unit circle. And that does not look like a circle, so I'm just going to redraw that there. Okay, that's better. Okay, so cosine is the x value, right? So here's our x and here's our y. And half would be about here. So that would be at pi over 3 and 5 pi over 3. So we're at pi over 3 and 5 pi over 3. And also any plus or minus any multiples of 2 pi for either of those, right? Because you can go a full 2 pi around, one revolution there, and you'll be back at the same spot. So anyways, so our cosine, our x value, is less than 1/2. So that means on the left side when we're in between these two. So one of the intervals would be pi over 3 up to 5 pi over 3. Okay, and non-inclusive, right? Because we have rounded brackets here because we only have a strictly less than, cosine x is less than 1/2, right? And then this is also in union with anything like when we add like 7 pi over 3, let's say, and if we add a 6 pi over 3, 11 pi over 3. These are also valid intervals. But when we look at our initial condition, remember, which was y of pi over 2 is equal to 1, pi over 2 is right here, and that's in this interval here. Okay, so that's the one we're going to pick for our interval of existence. And we can also just write this, or we could write pi over 3 and then write x in between this interval. And you do not add those equal or equal to signs because, remember, we said it's strictly less than, and we have these rounded brackets, so it doesn't include the endpoints. So you could either write this thing that I'm boxing, this inequality, or you could just rewrite this in parentheses, and that is all. Okay, for our interval of existence.
I need your love.